Alright, in this next section we're going to look at curvilinear motion. In the last chapter, we kind of saw a little bit of this type of application, but we were looking at rectilinear motion, and that's just motion along a straight line, so you can go back and forth. In this case, in this section, we're going to allow motion in 2 dimensions. And so we're going to consider things moving in 2 dimensions, which means we need to have some kind of working knowledge of vectors. A vector is something that has both magnitude and direction. So velocity is a vector, for example. So that's where we're going to use vectors to kind of describe this motion in 2 directions. It has the magnitude, which is just how fast, right? Its speed, but also its direction. And the direction is always expressed as an angle, usually, and for our class, it'll be an angle in kind of standard position, measured positive, in the positive direction from the positive x-axis. Or you can also give some acute angle with including a reference point, including some point of reference for that. Now, before we get into the calculus of all this, we're going to kind of just do a little bit of a primer on vectors. So as I mentioned, a vector has both magnitude and direction. So in the figure here on the right, we've got a vector. That vector is called v. In textbooks, they'll write it as a bold v, to kind of say that's a vector and not just like a scalar, a number. That's harder to do when you're writing things out. So I use a little, and it's pretty common to use like a little kind of half arrow over the vector to indicate that that's a vector quantity. So the vector is this guy right here. It's that kind of directed magnitude. It's got a length, that's the magnitude, that's the absolute value. And the angle theta, that's the direction. So when we give a vector quantity, we do so by providing magnitude and direction, and it's pretty common to give the vector as whatever its magnitude is, and then write like a little angle sign, and then whatever the measure of the angle theta is. That's a pretty common shorthand. But we can also categorize or define a vector by the coordinates where it ends, right? So these are called the components of the vector. Every vector has an x component and a y component. So what we're going to do is work on finding what those components are. And then if we know what those components are, I'm going to drop down this perpendicular here. If I know what the y component is, that gives me that length right there. If I know what the x component is, that gives me this length right here. And so we have this nice right triangle, and you can see why the magnitude is given by the square root of the sum of the squares. That's Pythagoras. And using SOHCAHTOA, since we have a right triangle, SOHCAHTOA applies, this right triangle trigonometry. We know that tan theta is Vy over Vx. And so if you're looking for the angle, you can use the arctan function. Now there are limitations to the arctan function. Arctan will never give you, for example, a second quadrant angle. So what we do is we find the reference angle, which is always an acute angle. It's always an acute angle, and you could find that reference angle by applying arctan to the Vy over Vx, but always positive. So that's why there are these absolute values here. That'll give you an acute angle, and then you can figure out where your vector is based on what quadrant it's in. So for example, if you know that your vector is in the second quadrant and what you want is this angle here, then what you're going to do is just subtract your reference angle from 180. If you're in the third quadrant, you will add your reference angle to 180 because you got to go beyond the 180. If you're in the fourth quadrant, you're going to subtract your reference angle from 360. And if you're in the first quadrant, you don't have to make any adjustments at all. The arctan function gives you the angle you want. So I'm just going to kind of summarize that. This is stuff that we've learned in pre-calculus. but it may have been a little while since the last time we've had to use it. So if you're in the first quadrant, your angle is just equal to the reference angle. In the second quadrant, your angle is 180 minus the reference angle. In the third quadrant, your angle is 180 plus your reference angle. And in the fourth quadrant, your angle is 360 minus your reference angle. So all of this doesn't require calculus, right? But we're going to use calculus to help us find out what these components are, right? So once I've got those components, we can use Pythagoras and arctan to get our, the important information about our vector. Calculus comes into play when we want to find those components. So imagine something is moving along in this fashion, right? Like the thing here I'm outlining in green, like that's the path of this object. And I want to know what its velocity is at some point, maybe right at this point right here. If it's sort of moving along this path, then at this point some of its motion is horizontal, some of its motion is vertical. And we find those components. The x component is the rate at which the x coordinate is changing. So it's dx dt. The y component is the rate at which the y coordinate is changing. So that is equal to dy dt. Some of the problems that we'll be doing, they'll describe the path by giving us a pair of equations. And we call these parametric equations. It's like one equation for y and one equation for x. And they're both given in terms of the time, t. And in those cases, it's fairly straightforward to find dx dt and dy dt. And for example, actually, let's just go ahead and do one problem. An object is moving by the parametric equations. X equals 3t squared and y equals 1 minus t squared. If you wanted to try to put together what the curve looks like, the idea is you let t range through a bunch of values, maybe starting at t equals 0, and maybe you go up by little steps, like maybe t goes up by 1/10 each time. And at each point, at each value of t, you just find the x and the y, and you know that those are the coordinates at that value of time. And then you do it again for the next value of time, and you get another pair of coordinates. If you have these parametric equations, finding Vx and Vy is fairly straightforward. Here they tell us that an object is moving by these two equations, x equals 3t squared and y equals 1 minus t squared. Distances are in centimeters and time is in seconds. We want to find the resultant velocity when t is equal to 2 seconds. So I'm going to start with the given equations. I know that x is 3t squared, so dx dt is 6t, and the x component, Vx, I'm going to get just by evaluating the derivative when t is equal to 2. They told me that's the value of time I'm interested in. 6 times 2, or 12. And then we do it again for the y function. So y is equal to 1 minus t squared. dy dt is negative 2t. So Vy is negative 2 times 2. Again, I'm just plugging in the value. In fact, maybe I'll write that out. I'm evaluating dy dt at t equals 2. So that's negative 2 times 2, or negative 4. Now look, the x component is positive and the y component is negative. That happens in quadrant 4. And so I'm just making a note of the quadrant because that's going to affect my angle. So now I've done, the calculus has served me as much as brought me as far as it's going to bring me. Now I'm going to put everything together using Pythagoras and arctan. So the magnitude is given by the square root of the sum of the squares of the components. Let's see, 144 plus 16 is 160. So this is the square root of 160. And, you know, it's an applied problem, so I think it's probably appropriate to get an approximation. I get 12.65. So the magnitude is 12.65, and the magnitude is where the units are attached. So the distances were in centimeters, and the time is in seconds. So this magnitude is 12.65 centimeters per second. Now, the reference angle is always arctan of the absolute value of Vy over absolute value of Vx. So I'm just going to plug in my components, Vy over Vx, but I'm making everything positive, 4 over 12. I'm going to put my calculator in degree mode. It's okay to use radians for your angle if you want. If you do that, then of course the adjustments you make for different quadrants will be from the pi and the 2 pi instead of 180 and 360. I think it's pretty conventional to use degrees when you're doing these applications with vectors. So I'm going to go ahead and just put my calculator in degree mode. So arctan 4 over 12. That is 18.43 degrees. Since this is in quadrant 4, I know I'm going to subtract that from 360. So we get 341.57. And now, just at the end, I want to give like a single answer. Like, here's my vector. So my velocity vector is 12.65 centimeters per second at an angle of 341.57 degrees. Okay. So, and some of the problems are like this one in that they'll give you the pair of parametric equations. Sometimes we get problems that are like this one where they describe the path by giving the rectangular equation we're used to. Rectangular equation just means y is a function of x. So here they've told us the path is 1/3 x squared. Now, they tell us the path, like we know what the path looks like, you know, as a graph. Some quadratic, it looks like a parabola, right, with its vertex at the origin. But that equation by itself does not work time into it. It tells us where it travels, but not when it gets to each point, right? That was one nice thing about the parametric equations, like the time was kind of baked right into the path. So here they've given us the rectangular equation, but then they give us extra information. They say that the velocity Vx is constant at 6 centimeters per second. So they're telling us how the x component changes, how the x coordinate of the location changes over time. And that it's constant at 6 centimeters per second. So we know that dx dt is always equal to 6. That's helpful information for us. I'm going to set that aside. So we know that Vx equals 6, right? We have our x component. We need the y component. Because once I've found the y component, then I've got both my components, and I can use Pythagoras and arctan. So the way we're going to get our y component is we're going to use this equation they gave us, right? We know here's the path that it follows. Y equals 1/3 x squared. And we are going to differentiate with respect to time, right? We want dy dt, not dy dx. So we're going to have to use our implicit differentiation skills here. So dy dt is equal to, I'm going to use the power rule as usual. This will be 2/3 x, and then times dx dt. That's incredibly important here. So we are differentiating implicitly. With respect to t. So now we have this expression for dy dt. And I want to be able to figure out what is vy. Now, we know that vx is equal to 6 because it was always equal to 6 and they told us. Dy dt seems to depend on where it is, right? What that x component is. And I can tell that it depends on x because I've got x worked out, involved in this expression. It also has dx dt involved, but this we know is always equal to 6. They told us it is, so we can plug that in. But then they also told us we're interested in what's going on at this point, at 2, 1.33. So I'm going to replace the dx dt with 6. Simplify this dy dt expression. 6 times 2/3 is 4, so it's 4x. And now to find vy, I'm just going to evaluate it at the point when x is equal to 2. And we get 8 for vy. We already knew that Vx is equal to 6. This is in quadrant 1 if they're both positive. So now we're going to find the magnitude and direction. Magnitude we get by using Pythagoras. So 6 squared plus 8 squared. We get 10. And our units, it's going to inherit the same units they gave us for Vx. So this would be centimeters per second. And this is in quadrant 1, so we don't have to make any adjustments. Theta is just arctan of 8 over 6. That's 53.13 degrees. So our velocity vector is 10 centimeters per second at 53.13 degrees. All right, so we know that we've been using the fact that velocity is the time rate of change of displacement. If I know displacement or position, I can differentiate with respect to time and get velocity. The time rate of change of velocity is acceleration. So we can also find acceleration vectors. Acceleration is a vector quantity. It has magnitude, it has direction, and we'll get the acceleration, the components of the acceleration vector by taking the second derivative with respect to time, right? If it's the derivative of velocity, that means it's the second derivative of displacement. So I've got a couple examples here. In example 3.6, they give us a pair of parametric equations. That's pretty nice. We've already got our equations in terms of t, so I don't have to worry about implicit differentiation. I'm going to differentiate twice and evaluate at t equals 2 to find my components. Really, these problems are just like the velocity ones. I just need to use the second derivatives to get my components. So here I'll just note that there's no units given in this problem, so we won't be attaching any units to our answer. Our x is equal to t cubed. So I'm going to find the second derivative. First derivative is 3t squared. Second derivative is 6t. And that means that the x component I'm going to evaluate when t is equal to 2. So the x component is 12. Our y function is 1 minus t squared. dy dt is negative 2t. The second derivative of y with respect to t is negative 2, is constant at negative 2. So that means ay is negative 2. And if I look at these values, x is positive, y is negative, I know that's quadrant 4. Now I have my, I've got my components, so we could finish this up with Pythagoras and arctan. So we got 12 squared plus negative 2 squared. That's the square root of 148. And if we approximate that, $12.17. We're in quadrant 4, so the angle, I'm going to do this all in one go. If it's in quadrant 4, I know I'm going to subtract the reference angle from 360. Excuse me. So I'm going to have 360 minus arctan of the y over x, but I'm going to make everything positive, so just positive 2 over 12. And I get 350.54. Alright, so now putting this together, our acceleration vector is 12.17 magnitude at an angle of 350.54 degrees. Alright, let's try one more. In this problem, again, they've given us a pair of parametric equations. We want both velocity and acceleration. So we're going to have to find two vectors. So I know I'm going to need both the first and second derivatives for y and x with respect to time. So let's do that part first. X is 45t, dx dt is 45, and the second derivative with respect to time is 0. So if dx dt is constant at 45, that means that vx is 45. The second derivative is constant at 0, and that means that ax is 0. So I know the x components for both velocity and acceleration now. Let's do the same for the y function. Y is negative 4.9 t squared. So dy dt is negative 9.8 t. And I know that the second derivative is constant at negative 9.8. So, looking at that second derivative, I know that if that's constant at negative 9.8, then the y component of velocity is negative 9.8. The first derivative is negative 9.8 t. We are interested in velocity and acceleration when t is 3 seconds, so I'm going to evaluate that when t is 3. So I get negative 29.4. Now, I think we've done all the calculus that we need to do. So let's put this together. Let's do our velocity vector first. We know that Vx is 45, Vy is negative 29.4. So again, that is quadrant 4. Our magnitude, we're going to use Pythagoras. Oh, negative, I dropped that off. Negative 29.4 squared. $53.75. The units here, distances are in meters, time is in seconds, so this is meters per second. And it's quadrant 4, so theta is 360 minus arctan of positive y, 29.4 over 45. And that is 326.84. So our velocity vector is 53.75 meters per second at an angle of 326.84 degrees. All right, let's the last thing we want to do is find acceleration. And we know that the x component is 0. The y component is negative 9.8. Now, you can use Pythagoras to get the magnitude always. That'll always work. But I just want to point out we can also do that conceptually here. So here we are in the plane. This is a y component of negative 9.8, an x component of 0. That means that it's straight down. So the length of that is just going to be the y component. Right, this length is 9.8. That's what puts it at a y component of negative 9.8. The angle we kind of have to do conceptually. Because the x component is 0, you know, in the arctan function we put the y component over the x component. We can't divide by 0, but we can do this conceptually. That angle is definitely 270 degrees. So we know that our acceleration vector is 9.8 meters per second squared at an angle of 270 degrees.